The Earth has a thin, rocky crust. The continental part of the crust is a good bit thicker than the oceanic part of the crust. Chemical composition is a little bit different as well. The continental crust being made up of granitic type bedrock and the oceanic being made up of basaltic type bedrock. Beneath the crust, you've got the mantle, more rock. Beneath the mantle, the outer core, liquid iron, and then finally the inner core, solid iron. When we look at the chemical composition of the crust, we discover that oxygen's number one. It really shouldn't be too big a surprise because oxygen's a very chemically reactive substance and it reacts with the other things such as silicon, aluminum, and iron. A mineral is a natural chemical substance. As a substance, it has a definite chemical composition and physical properties that characterize it. We can subdivide the minerals into those that have silicon and those that don't. We can further subdivide the silicates into those that have significant amounts of iron and magnesium, the ferromagnesians, and those that don't, the non-ferromagnesians. The ferromagnesian minerals tend to be dark green or black in color. Olivine, pyroxene are common ferromagnesians. Amphibole and biotite are two more common ferromagnesian minerals. The biotite of black mica has a two-dimensional sheet structure. Non-ferromagnesian silicates tend to be a little bit lighter in color and less dense than the ferromagnesians. Feldspar is the most abundant mineral in the crust, and quartz the second most abundant. Both muscovite and the clay minerals have a two-dimensional sheet structure. However, the clay minerals, the sheets are microscopic. Three of the most important non-silicate minerals are calcite, good old calcium carbonate, main ingredient in limestone, halite, which is sodium chloride, table salt, and gypsum, calcium sulfate dihydrate. The hemihydrated gypsum is known as plaster of Paris. Rocks, which are a mixture of various minerals, can be divided into three basic types on the basis of how they were formed. The igneous rocks are formed directly from molten materials such as magma or lava. Your metamorphic rocks are rocks that have been changed by heat and pressure from their original form. And sedimentary rocks are rocks that are generated from fragments, pieces of other rocks, or rocks that have been dissolved and then reprecipitated. The three basic types of rocks can all be interconverted. If you take sedimentary rocks or metamorphic rocks and melt them, you've now got an igneous rock. If you take an igneous rock or a metamorphic rock, erode it, then go through the process of lithification, you've now got a sedimentary rock. If you take an igneous rock or sedimentary rock, treat it with heat and pressure, you can generate a metamorphic rock. As the molten material cools, crystals of the various minerals begin to form. These crystals grow and grow until all of the molten material has been consumed. Three of the most common extrusive igneous rocks are basalt, andesite, and rhyolite. We mentioned basalt earlier as the basic bedrock of the oceans. Both obsidian and pumice have got quite a bit of silica in them, that is quartz. And when you've got a lot of silica in the lava is very viscous. In the case of obsidian, the lava solidifies very quickly, giving you a glassy texture, microcrystals. In the case of pumice, you've got lava that had a lot of gas in it, and as that gas was bubbling out, the lava solidified. Gabbro, diorite, and granite are the intrusive counterparts of basalt, andesite, and rhyolite. Intrusive rock formations are known as plutons. A batholith is simply an extra special big pluton. A dike is a pluton that is cut vertically through other layers of rock. A sill is cut horizontally in between layers of other rock. And a laccolith is kind of like a sill, only it's kind of pushed up in the center. One of the most common types of metamorphic change is in terms of crystalline form. And foliation is one of the more common types of crystalline form changes. If you've got ferromagnesian minerals in the rock, the pressure can squeeze them into banded or layered arrangements that we call foliation. Slate, schist, and gneiss are three very common foliated metamorphic rocks. Quartzite and marble are common non-foliated metamorphic rocks. The Earth has written its biological history in the sedimentary rocks. The sedimentary rocks can be formed by both physical and chemical processes. In the physical processes, you're taking the material and compressing it, and then, in some cases, recrystallizing it. In recrystallization, you're dissolving the crystals and then reprecipitating them out. In the chemical processes, some of this precipitated material can help glue the fragments together to form a solid rock. We can subdivide the sedimentary rocks into two basic categories depending on what they're made up of. If they're made up of little pieces of other rocks, then they're fragmentals. If they're made from recrystallized material, then they're precipitates. Three common types of sedimentary rocks are shale, which is made of very fine materials, muds, sandstone, made of sand-type material, and conglomerates, made of a little bit bigger stuff, more than about 2 millimeters across, gravel, pebbles, things like that. Two common precipitated sedimentary stones are chert and limestone. Now, chert's made up of microscopic crystals of quartz. Quartz not terribly soluble in water, and so it's going to take a long time to form any chert. Limestone, well, the calcite's a good bit more soluble than water, as people in Spring Hill are finding out with their sinkholes. But even with the limestone, it's going to take quite a bit of time to dissolve enough calcium carbonate so you can then reprecipitate it to form the limestone. Both chert and limestone are often of biological origin. About 200 years ago, scientists realized that the rock cycle was constantly reshaping the face of the Earth. New mountains were being formed, old mountains were being worn down all the time. Volcanoes can be divided into three basic types: shield volcanoes, cinder cones, and stratovolcanoes. Shield volcanoes can be recognized by their gently sloping sides. Mauna Loa, Kilauea are typical large shield volcanoes. Shield volcanoes tend to have gentle eruptions of basaltic lava flows. Cinder cones, on the other hand, are pretty much the opposite of your shield volcanoes. They have steeply sloped sides, rarely exceeding 1,000 feet in height, and have violent pyroclastic eruptions. Lots of gas is released. Their eruptions are a lot like taking the top off a carbonated beverage. Rock, dust, ash, cinders get thrown high into the air. Stratovolcanoes like Mount Fuji, Mount St. Helens, and Vesuvius combine eruptive features of both shield and cinder cones, and they are the most dangerous type of volcano. The greater the viscosity of the magma and the more gas you've got in the magma, the greater chance you've got for a very violent eruption. In your volcanic gases, water vapor is number 1, carbon dioxide is number 2, with smaller amounts of nitrogen, hydrogen, and various sulfur compounds such as sulfur dioxide. Weathering is a process by which exposed rocks on the surface of the Earth break down. We can have chemical weathering where you have oxidation or attacked by acids, and then mechanical weathering. Now, one of the things you may have noticed is if you ever had rust on your car bubble up the paint, well, oxidation can cause changes in volume, and this can also do the same thing it does to your paint on your car, can break apart the rock. Erosion is breakdown and transport of materials. Stream erosion is the most important type of erosion on the face of the Earth. Fast-moving rivers tend to downcut rapidly, and so your mountain streams tend to do a lot of downcutting, but as they downcut, this decreases the slope. This river slows down. As the river slows down, you tend to have more side cutting taking place. It cuts into one bank, piles a sandbar up against the other bank. If you keep this up long enough, you end up with a wide floodplain and a meandering river. As a glacier moves, it tends to pick up bits of rock and uses these rocks as sandpaper. As the glacier moves, it drags these rocks along, grinding them against the rock surfaces that it's sliding along, smoothing and giving parallel scratches to the remaining rock surfaces. When the glacier melts back, all this debris gets dropped, and so you find these rocks that have gotten one face ground off of them, a flat side. Your valley glaciers tend to generate a U-shaped erosional feature. Flat valley floor with very steep sides. Think of Yosemite. You got steep cliffs and waterfalls in Yosemite. Mountains are a bit like icebergs in that there's an awful lot of the mountain underground that you don't see. Now, as erosion wears away the rock of the mountain, that unseen part of the mountain floats upward. And so the mountain doesn't wear down quite as quickly as you'd expect. The water table is simply the top of the saturated zone. The aquifer is a layer of porous rock that's saturated with water. Limestone is relatively soluble in water, and so over long periods of time, slow movement of water through the aquifer can erode the limestone to form caves. Rivers, glaciers, ocean currents, and groundwater each generate their own characteristic types of deposits of sediments. Anytime a river slows down, it's going to drop some of its sediments. If you've got a river that's going around a curve, one edge of the curve is going to be going faster than the other edge. On the edge that's going faster, you get side cutting. On the side that's going slower, you get a sandbar. And of course, if you keep this process up for a long time, you generate a floodplain, as we mentioned earlier. An alluvial fan's kind of an interesting feature. If you got a mountain river, it's running fast, but then what happens when it gets down the plain? Well, it slows down. And so right at the base of the mountain, you can drop some of your sediments and generate an alluvial fan. Similar sort of thing happens when the river runs into the ocean. The river slows down, drops a lot of its sediments, and you generate a delta. Glaciers generate two types of sediments. Till, which is all the stuff that was dropped directly by the glacier. You get a wide assortment of sizes of things. And outwash. This is the debris that was washed away by the melting water from the glacier. The ocean currents carry more sediments than all the rivers put together, which is not surprising considering the size of the oceans and the ocean currents. Now, everyone's familiar with beaches and sandbars, the deposits the currents make along the coastline, but an awful lot of these sediments also get dumped down on the continental shelves. The minerals dissolved in your groundwater can of course precipitate back out, filling the pore spaces of sediments, generating new sedimentary rock, can fill in the cracks in rocks with mineral veins, and of course generate beautiful stalactites and stalagmites in caves. There are two basic ways a crust can move: folds and faults. With folds, you're bending the rock. Obviously, this is a rather slow process. If the rock bends upward, we call it an anticline. If it bends downward, we call it a syncline. With faults, you're breaking the crust, and one piece of the crust moves relative to the other. We got a normal fault. This is a fault generated by tension, a pulling apart. The rock moves apart, and one piece slides down relative to the other, generating a fault scarp, a little cliff. Thrust fault, just the opposite. Compression breaks the rock, one piece of the crust slides upward relative to the other, and once again generating that little overhang, that little fault scarp, little cliff. Strike slip fault, on the other hand, the rocks are moving parallel to each other in opposite directions. And this is a type of fault that we got out in California with the San Andreas fault. Most earthquakes occur when you have movement along a fault. Now, these movements generate vibrations we call seismic waves. One of the things we can't do very well yet is make good short-term earthquake predictions. We can't say that, oh, well, next Tuesday at 1 o'clock you're going to have an earthquake. However, we do know that the reason the rock moves is because stress is being placed on it. And if we can measure that stress accurately enough, then someday we may be able to make good short-term predictions about earthquakes. We can divide seismic waves into two basic categories: body waves, waves that go through the earth, and surface waves, waves that run across the surface of the earth. Primary body waves are longitudinal pressure waves, like sound waves. The vibrational motion, compression, and rarefaction is in the direction of motion. Now, anytime a wave travels from one type of material to another, the wave refracts or bends. And it turns out that when these pressure waves go from the mantle to the outer core, they get bent enough to where a gap opens up. And we call this gap, where you don't detect any primary body waves, a shadow zone. Secondary body waves are transverse waves. That is, the motion is 90 degrees the direction of travel, sideways vibration. Now, transverse waves can only pass through solids, not liquids or gases. So when the secondary body waves hit the outer core, they stop. The outer core is liquid. And so there's a large region on the other side of the Earth where you don't detect secondary body waves. Geologists have a number of different magnitude scales for earthquakes. There's surface wave magnitude, moment magnitude, and of course the most famous of all, the Richter scale. All of these scales are logarithmic. Each step's a factor of 10 in size of the wave, that is vibrational amplitude, and a factor of 30 in energy. That means a magnitude 8 earthquake packs 30 times the energy of a magnitude 7. Although California is famous for its big earthquakes, there are other areas in the United States that have the potential for great earthquakes. And one of these is New Madrid area of Missouri. In 1811, there was a great earthquake, followed by 2 more in 1812. The major component of the mantle seems to be igneous-type silicate rocks with large amounts of ferromagnesian minerals. We think the core is most likely made of mostly iron with smaller amounts of other things. And our reasons for this is indirect evidence. No one's ever drilled down to the core. However, our indirect evidence says iron fits the bill. Earthquakes and volcanoes are powered by geothermal energy. This geothermal energy comes from radioactive decay down deep in the earth. The Earth's magnetic field is generated through a dynamo effect by the convection down the liquid core. Now, convection currents can change over time, so it's not surprising that the Earth's poles are constantly wandering. In fact, not only do they wander, but they occasionally flip. The North Pole becomes the South Pole, the South Pole becomes the North Pole.